Welcome to The Explainer. Today we're going to talk about a really powerful statistical tool that helps us think a lot more clearly about uncertainty. It's all about how we can use math to update our beliefs when we run into new information.
All right, let's just jump right in. I've got a scenario for you, and it's one that might seriously mess with your intuition. It's a classic for a reason. It really shows you just how counterintuitive probability can be.
So, picture this. You go and take a medical test. It's supposed to be 99% accurate, and it comes back positive. What's your first reaction? You're probably thinking, okay, shoot, there's a 99% chance I have the disease. I mean, that makes sense, right? Well, maybe not. The actual answer is way more surprising and honestly a lot more interesting.
So to figure this puzzle out, we can't just go with our gut. We actually need a specific tool for the job. It's a mathematical formula, and its whole purpose is to help us update what we believe when we get new evidence.
And that tool? It's called Bayes' theorem. At its core, the idea is actually pretty simple. It's just a formal, kind of structured way to adjust what we think we know based on new stuff that we learn.
And listen, this is not just some dusty old idea from a math book. Nope. This is the engine running behind the scenes on so many things you use every single day. Think about the spam filter in your email, or how Netflix knows exactly what you want to watch next. That's Bayes' theorem at work.
Okay, so let's actually look at the formula now. I know. It might look a little scary at first, but I promise you we're going to break this thing down piece by piece, and it's going to make perfect sense.
And here it is in all its glory. P of A given B equals P of B given A times P of A, all divided by P of B. Don't worry about memorizing it just yet. We're going to talk about what all these letters actually mean.
Okay, this slide right here is super important. This is where we translate that math speak into plain English. Think of it like this. PA is your initial belief. It's what you thought was true at the beginning. Then comes PB/A, the new evidence that shows up. PB is kind of a reality check, a normalizing factor that keeps things grounded. And all of that leads us to PA/B, the grand finale, your updated belief. It's a much smarter, more informed version of what you started with.
All right, you with me? Let's see how this all fits together. We're going to take this exact formula and use it to finally solve that medical mystery we started with. So let's start with a nice round number. Imagine we've got a group of 1,000 people. This is our whole population.
Now, in this group of 1,000, the disease we're testing for is actually kind of rare. Only 100 of them are actually sick. The other 900? Perfectly healthy. And this is a really important piece of the puzzle. Keep that in mind.
Okay, so what happens when all 1,000 people take our 99% accurate test? Well, this table breaks it down perfectly. Look closely at the errors. They're small, but they're so important. Out of the 100 people who are actually sick, 99 get a correct positive result, but one person gets a false negative. They're told they're fine when they're not. On the flip side, out of the 900 healthy people, most get a correct negative result, but 9 of them get a false positive. They're told they're sick when they're actually healthy.
So first things first, let's figure out our initial belief. That's the P of A in our formula. What's the chance that any random person from this group is sick before they even take the test? Well, it's 100 sick people out of 1,000 total. That's 10%, or 0.1.
Next up is the new evidence, the P of B given A. This is just the accuracy of the test. What's the probability of getting a positive result if you're actually sick? We already know this one, right? The test is 99% accurate, so the probability is 0.99.
And finally, we need that reality check, the normalizing factor, P of B. This is just the total chance of anyone getting a positive test for any reason. So we have to add up the 99 people who are sick and tested positive and the 9 people who are healthy but still tested positive. That gives us a total of 108 positive tests out of the 1,000 people. So that's a probability of 0.108.
Okay, here's the moment of truth. We take all those numbers we just found and plug them into the formula. So we take 0.99, multiply it by 0.1, and then divide the whole thing by 0.108. And what do we get? The actual probability of being sick after getting that positive test is only about 91.7%.
Whoa! Wait a minute. That is way lower than the 99% we started with, right? So what's going on here? It all comes back to how rare the disease is. Because so few people actually have it, even that tiny number of false positives, those 9 healthy people who tested positive, they end up having a huge impact on the final number.
So we've done all the math. What's the big takeaway here? Why does this matter?
Well, what this really shows us is that your starting point, your initial belief, or what statisticians call the base rate, is incredibly important. New evidence, even really strong evidence, doesn't just wipe the slate clean. It just updates what you already believed. That initial 10% chance of being sick, it acts like an anchor, and the new evidence just pulls it in a new direction.
And that brings us to the final idea I want to leave you with, Bayes' theorem. It's not just for data scientists. It's really a powerful tool for thinking, a mental model that any of us can use. It's a way to think more critically about the world, to really question our own assumptions, and to be willing to change our minds when the evidence tells us to. So my question to you is, what beliefs in your own life could you reevaluate using this way of thinking?